Hi, I'm Reza, and this is a very short tutorial on convolutional neural networks. Let's start off with a very famous computer vision challenge called ImageNet challenge. ImageNet is a very huge data set of images, around 14 million images in 20,000 categories. And there's been a long history of different methods winning this challenge. But in 2012, AlexNet won the challenge. AlexNet was the first CNN-based uh, algorithm to win this challenge. And basically, many people think that this was one of the main, let's say, achievements that triggered this huge improvements and revolution in AI using deep neural networks. And by the way, AlexNet was developed by Professor Jeffrey Hinton in U of T. And after that, and you see all the winners at the end uh, used convolutional neural networks with deeper and deeper architectures. See, AlexNet has 8 layers, and then we have the next layer again, another architecture with 8 layers, VGG with 19 layers, GoogleNet with 22 layers. And at the end, we have the winner of 2015 with 152 layers. So uh, let's see how convolutions work and why can we use them in such deep neural networks. So let's say we have a very, very simple fully connected layer. We have only, let's say, one hidden layer. And in ImageNet, what we have is we have images of 224 pixels. And because we have 3 channels, we have around 150,000 uh, pixels. Let's say we have a hidden layer of size 5,000 nodes, and because we have 20,000 categories, at the end we have the output layer basically has 20,000 nodes. So a simple calculation shows that the first layer, basically this one, needs around 750 million weights, and the last layer basically has 100 million weights. So in total, we have around, let's say, 850 million parameters in this model. And if you remember, we had around 40 million examples. So basically, clearly, such fully connected layers cannot scale. So let's see different parts of a convolutional layer. We'll start with filter parameters. So basically, in this example, let's say we have 32 by 32 images, and we have basically 3 channels because we have color images. And a filter is basically, let's say, a number of parameters with the size of a small patch of the image. So basically, let's say we have a filter of size 5 pixel by 5 pixel with 3 channels. So every element of this, let's say, three-dimensional tensor are filled with parameters. And the important point here is that, as you see, we always have the same depth between the image that the filter is working on and the filter itself. The convolutional operation is basically putting this, let's say, kernel or this filter over the image and calculate the inner product of the parameters and the pixels of the input image to get one scalar value. So this is called one convolutional operation. So in general, a convolutional operation consists of moving this filter uh, into different parts of the image. So basically you start from this part of the image, you move this filter, and at each point you calculate this, let's say, dot product between the filter parameters and the image pixels. And at each point, the filter parameters are actually the same. You're just moving this kernel or this filter over different parts of your image. So we convolve or slide this kernel or this filter over all spatial locations. So what we get at the end is, let's say, because we had 32 by 32 input image and 5 by 5 filters, at the end what we will get is 28 by 28 activation maps. And as you see, the depth of this activation map is always 1. The reason is, as mentioned earlier, the depth of the filter and the input image are the same. So at each spatial position where you put your filter, what you get is a single scalar number. Well, we can have another filter with the same size of 5 by 5 by 3, and what we get is another activation map, and we can stack this together. So let's say, as an example, we have 6 of these filters. So what we get is basically an output of 28 by 28 by 6, and each of these slices or each channel represents the output for one filter. So we had 32 by 32 by 3 input images, and the output we get is 28 by 28, and because we had 6 of these filters, it's 28 by 28 by 6. And by the way, why 26? The reason is we had 5 by 5 filters, and there are only 28 positions that you can put a 5 by 5 filter in a 32 by 32 input image. So the reason is, so we get 32 minus 5 plus 1, which will be 28. So that's where this 28 comes from. And let's look at the number of parameters we have. For each filter, we have the size of the kernel is basically 5 by 5 by 3, and this 1 is basically the bias term. So for each filter we have 76 parameters. In total we had 6 of these filters, so at the end we have 456 weight or parameters for this, and this basically creates one convolutional layer for us. So we have so the input of this convolutional layer is 32 by 32 by 3. The output is 28 by 28 by 6, and in total we have 456 parameters. We can stack this convolutional layer together pretty much the same way that we stack fully connected layers. So we have convolutional layers followed by activation functions. In this case, or in most cases, ReLU functions. So let's take a closer look. So again, the input is 32 by 32 by 3. We have 6 filters, each size 5 by 5 by 3. And this 3 basically comes from here. So at the end, what we saw is that we get 28 by 28 by 6 outputs in this layer, and we pass this through an element-wise ReLU. like fully connected layers. Let's see the next layer. For the next layer, we have 10 5 by 5 by 6 filters or kernels, and this 6 basically comes from the depth of the input. And again, what we get as the output of this layer is 24 by 24 by 10, let's say, activation maps. And these 10, the reason we have 10 here is that we simply had 10 filters here. And this is basically, this 10 here is just a design choice. This is how we designed our, let's say, architecture. The important thing here is that the depth of each of those filters should be equal to the depth of basically the input activation maps. And we can stack as many as these convolutional layers followed by activations together to form a convolutional neural network. And again, this 24 basically comes from 28 minus 5 plus 1. Okay, let's take a closer look at convolution operation and see what this stride parameter means here. So basically, a stride is the amount of jumps or steps you move the kernel at each convolution operation. So if a stride is 1, your filter here, the green box, moves 1 pixel at a time. So as you see, because we had 7 by 7 input images and 3 by 3 kernel size, what happens is that we can get only 5 positions. So the output is again 5 by 5, as you see. Now what if stride is 2? Our kernel just jumps 2 pixels at a time. And that's why the output we get is 3 by 3. So basically the size of output we get is a function of input size, filter size, and stride. If you want to calculate the output, as I said, as a function of stride input and kernel size, this is the formula that we can come up with. N is basically input size, F is filter size, and we have a stride. So N minus F divided by a stride plus 1. However, note that this division here, you should take the floor of the division, because in case of, for example, if a stride is 3, you might get floating point output sizes, which is obviously not correct. So, for example, in case of 3, what we get here is 7 minus 3 is 4. 4 divided by 3, the floor of it would be 1, and 1 plus 1 is 2. And if you work it through this example, this visual example, you will see that what we get is 2 by 2, because this is one position, and if we jump 3, we get the next one here, and we cannot move further. So these are all the 4 positions that we can place our kernel. So we will get a 2 by 2 output size. Now, in order to preserve image size and save us some time and confusion from calculating output sizes, one option is to zero pad the input. For example, let's revisit the example we had before. If we have a 7 by 7 input, 3 by 3 filter, and a stride of 1, if we zero pad, here you see this gray pixels here. If we zero pad our input, what we get as output here in the new, let's say, zero padded input is again a 7 by 7 output. So here we can preserve the output size by zero padding. So in general, if we have a filter of size f and with stride 1, we need to zero pad with f minus 1 divided by 2 pixels to preserve uh, the output size. For example, if we have a filter of size 3, we need 1 pixel, basically zero padding. If we have 5, input is 5, we need 2 pixels zero padding, and if input is filter is 7, we need 3 pixels zero padding. Now let's take a look at another example. Let's say the input size again is 32 by 32 by 3, and we have 10 filters, each of size 5 by 5 by 3 again, and we're using a stride 1, and let's say we have zero padded input with 2 pixels. So let's say we want to first calculate the output dimensions. So the input is 32 by 32, and we have 2 pixels zero padding. So here what we need is to calculate the zero padded out basically size. So this will be 36 by 36 by 3. The reason is we have 2 pixels zero padded, 2 at each side will be 4 pixels in total, so we have 36 by 36. And now from this we get 36 minus 5. Stride is 1, so we don't need to divide this by 1, and plus 1. So we get again 32. As you see, the input size is basically preserved. So what is the number of parameters here we have in this convolutional layer? We have basically 5 by 5 by 3 is the size of the kernel. 1 is, because we have bias for each of those filters, we have one bias term, one scalar. And because we have 10 of these filters, we multiply this number by 10, and at the end we get 760 filters. Another case that we can visit is using 1 by 1 convolution filters. So in that case, each filter is a 1 by 1 by 64. The reason is we have, as input, we have 64 channels, and in this case each kernel is a 1 by 1 by 64 let's say tensor. So this is what we're basically looking at as one filter at this position, and this will get basically moved into different parts of this input. And for each of those filters, we get again a 56 by 56 output, and because we have 32 of them, we will get as a result a 56 by 56 by 32 output. So each filter is performing a 64-dimensional dot product. Another building block of convolutional neural networks is pooling layers. Pooling layers basically perform downsampling operations, and the most commonly used pooling layer is called max pooling. In max pooling, what we do is we put a window of size, let's say in this example 2 by 2 here, and what we do is we basically pick the maximum value that this window can see in this image. For example, in this case, when our window is put in upper left corner of the image, the maximum element is 6, so we only keep 6. Now we have a stride 2, so we basically move our window into the upper right corner, and the maximum value we get here is 8. So we perform this downsampling approach by taking the maximum value of each window, um, and this is called max pooling. And an important thing to note here is that pooling layers does not have any parameters, so they're just performing some stationary, let's say, operation regardless of the. So they basically do not have any parameters to be learned. So they're just like a function performing a static function over their inputs. And as I said, they basically performing this downsampling operation. So if you have, for example, here 224 by 224 by 64, let's say tensor or activation map at this point, a max pooling will result in 112 by 112 by 64 output. And as you see from, for example, the activation map of one channel here, we are looking at only one channel. And what we are seeing is basically it's very similar to downsampling, this activation map. And pooling layers perform over each separately over each channel of the input. So convolutional operators or these filters perform over all the basically input channels at the same time, but pooling layers perform over each slice or over each channel separately. So if you look at an architecture of convolutional layers, this is what we see. We always have convolutional layers followed by ReLUs. Again, for example, another convolution, another ReLU, and after a bunch of convolution and ReLUs, we see a pooling layer. And we basically repeat this procedure. We have convolution ReLUs, and again pooling. So what this architecture learns is that in the first few layers learn very primitive filters. Let's say they basically learn edge detectors, or they are sensitive to, let's say, for example, edges. So they're sensitive to very basic and local, let's say, pattern in images. Like, for example, as I said, like, for example, horizontal edges or vertical edges or specific colors. And as we build up these activation maps, as we, let's say, combine them together, our model starts to learn more complicated patterns in the deeper layers. And for example, if you look at the final layers, what final layers are detecting or are sensitive to, they might be very complex patterns, like, for example, let's say wheels of a car, or for example nose or eyes of a human face, something like that. So this hierarchy in convolutional neural networks is something that is very common and very nice in these architectures.